Salutations. So we did the homogeneous one. So remember, homogeneous one looked in general like this. Linear second order equation with constant coefficients, right? This looks like this. That's a homogeneous one. So now we're going to do the non-homogeneous one. That means that this will become a forcing function f of x. But in this topic, in this section, we're going to do a forcing function of a very special kind. So let me therefore write the form that we will look in. Let me get to this one. So I will do it black now. We will look at something of the form E alpha x px. And this is a polynomial of a certain degree. We talk about that. That will play a role a little bit. And then E is an exponential function with an alpha that's going to play a role also. And so we're looking for general solutions of this kind of questions. And of course, we know that the theory says what we need to do is find a particular solution, and then the general solution is that particular solution you found plus the general homogeneous solution. Okay. So I'm going to do, so the easy case, well, easier case is that if there is no E alpha, so in other words, if alpha is 0, that means we have just ay prime double prime plus by prime plus cy equals a polynomial. Okay. And then what we do is we propose a solution of the form ax to the, okay, let me start from the lower terms. We can write a polynomial in ascending or descending order. I'm going to write it this way, cx squared plus something like that. The dot means, okay, we're going to stop somewhere, right? But I'm going to make precise when we stop. So, and these a, b, and c we call general coefficients. We have done this already in 5.3 and we have done it before. So these general coefficients are then, that's the section, this section's official title is actually the method of indeterminate coefficients or general coefficients. That is exactly, so okay, general, so the textbook called it undetermined coefficients. And how do we determine them? Simply by plugging that in. Okay, that's going to be the idea. But there are little things that we have to be careful of. So the first thing, which I haven't really made explicit yet, is how far do we go? How many terms do we take? Up to which degree do we go? Right? We have to address that. And there's a couple of other things that we have to talk about. So let's jump in right away with an example. So here is a simple example, y double prime plus y equals, let me take a quadratic here, x squared plus 4x plus 1. I took a rather simple homogeneous one. So let's solve this. So the step one, the textbook in this section doesn't talk about homogeneous solutions, but we should do that. And in the homeworks, actually, they do ask you to do that. So let's solve the equation in general, and perhaps even with I'm going to impose some, perhaps not very, I didn't check here what I should take as to make the numbers nice. So I'm going to put even initial conditions there. So this is the kind of question you can get. How do we solve this? Okay. First of all, we know that we always have to first look at the complementary homogeneous equation, which is y double prime plus y equals 0. Okay, we ignore the forcing function. Now this one, in turn, we have to look for because the second order linear with constant coefficients, and that's only when you have linear with constant coefficients. So for later, when we see other things, don't get confused here. So characteristic equation is t squared. What is the coefficient in front of t? Well, that would be the coefficient in front of y prime, but there is none. So same here. So we have t squared plus 1 equals 0. Don't write t here, right? Because The second derivative corresponds to the second power. The first derivative, which is not there, so there's no t there, and this is the zeroth derivative, so corresponds to the zeroth power, okay? So what is this? We know what this is. This is t squared minus 1. We know that the two solutions are plus and minus I. Minus I. So what is therefore the homogeneous solution look like? The general homogeneous solution. Let's think about it. So in general we wrote the solutions as lambda plus omega I. If these were the two roots, the conjugate roots, plus and minus, with this was called the real part, and this was called the imaginary part, then we know that the solution would be either E lambda x cosine omega x and E lambda x sine omega x. So what is the lambda in this case? Is there a real part? No. So lambda is 0, which means there is no E. Okay, that's good. What about the imaginary part? What is that? Well, is it I? No, remember, imaginary part is the number in front of I. So here it's also 1. So both lambda and 0, so in this case lambda is 0 and omega is 1. So this becomes just cosine x plus sine x. So this is how the general solution looks like. Oh, a cosine x plus b sine x. With a and b are still constants to be determined. We're going to use a and b in different situations, but we keep always our calculations separate, so that an a in one case, in one step, is not an a in the other step. It's just the book uses C1, C2, and C3, but that's more writing and prone to errors. So okay, that is the stuff that we know already. But now the particular solution, and here it is we have to do what I suggested here. We're gonna find so we propose a solution of the form a polynomial. And what is the polynomial going to be? Here, the polynomial is going to have the same degree as the polynomial here. So, a general polynomial degree 2. I'm going to write it again in descending order. Oh, not D, C, because that's the more familiar way that you write a polynomial. But it's not necessary. So this is what I'm going to propose the solution. So I want to say this is the same degree as the forcing function. Okay? Good. How do we solve this then? Well, we have seen this. We just start taking derivatives. 2ax plus b, and that's double derivative is 2a. And now we plug this in. We plug this in into our equation here. We plug this all in into this equation. So we get 2a plus, well, the y prime is not there, so plus y, this is ax squared plus bx plus c, so that is, I did this part now. Now I have to write this one, just copy, x squared plus 4x plus 1. And the method of indeterminate coefficients now says, okay, you have at the right hand side the polynomial, the coefficients of which you know. On the left hand side you don't know the coefficients, but these two polynomials are the same, so you just compare coefficients. So this is the technique called comparing coefficients. There are other ways of solving this, but in this case that's the easiest way. That means that you should rewrite this here and group this in powers of x. So this is ax squared plus bx plus 2a plus c. And so it becomes very simple now. Compare coefficients, the a with the 1, so a is 1. The b with the 4, b is 4. And then finally 2a plus c, we compare that with 1 here. And of course we know that a is 1. Let me do the calculation here now. A is 1, so we plug that in. 2 plus c is 1, so we see c is minus 1. And there we are. So our particular solution, I'm going to put the p now, because that's what we're looking for, is of the form x squared plus 4x minus 1. Okay? Don't start saying, oh, could I have guessed this? No. I took a very, very simple example. I'll do a bit more where you see the numbers really change. So what is now finally putting everything together? Step 3, right? What is our general solution? Well, that's this particular solution, x squared plus 4x minus 1 plus the general homogeneous solution was versus a sine x plus b cosine x. Well, I switched a and b around. Okay, that's no big deal. And then we had initial conditions. That was if x is 0, then y was supposed to be 1, and y prime also 1, I think. Whatever. Oh, y was 2, I said. I don't know why. Okay, so we plug that in. This is y, right? So if I plug this in, these two first, okay, then 2 is equal to minus 1. The sign of 0 is 0, so they only have a b left, plus b, so we see that b is 3. Okay, and then to plug in this one, we need the derivative, so we take the derivative again. Y prime is 2x plus 4 plus a cosine x minus b sine x. The derivative of cosine is minus sine. And now we plug in x equals 0. On the left hand side we get 1, that is what this tells us. And here we get 4 plus a, that is now 1, and this is 0. So we see that a is minus 3. And so the solution of the problem was y equals x squared plus 4x minus 1 minus 3 times sine x plus 3 times cosine x. Okay, so far so good. I'm not going to do, let's jump, there is one complication. And let me explain this complication here, what is going on. So here's another example. So suppose we have this example, y double prime plus y prime equals 3x plus 4. I'm going to, just for simplicity, take here degree 1. Well, let's do it just to degree 2, just to see that, yeah, there's no reason that I have to do degree 1 here, just degree 2 again. Let me not do the initial conditions here. What is the issue here? The issue here is that there is no y term. So let's look at well, we have I'm going to start, well, let's solve it in general because it's very quickly. The complementary homogeneous equation, okay? What is that? Well, that is y double prime plus y prime equals 0. And so the characteristic equation here is t squared plus t equals 0. You see, there is now, the difference with the previous case is we have no y. We have a y prime but no y. So this is what we get. So we get t times t plus 1 equals 0. So we get roots t equals 0 and t equals negative 1. Now the issue is this guy. And t equals 0 is a root. And why is it a root? Because there is no constant term, because there is no y. So no y term in the homogeneous part, in the linear, in the y part. And that changes things. If there is no y term, so what would we normally do? So, okay, continue here a little bit. So step 2 here, I'll do the rest of the calculation here. We need some work here to do, but I want to already jump to the real thing that changes here. So we would propose, well, we would say a general polynomial of degree 2, right? ax squared plus bx plus c. So this is the same degree. Again, this is 2, but it could be any degree here. So I wanted to take something else, but I'll do it in the next example, take a different degree. So we take the same degree, but since there is no y term, we have to multiply here with x. So our solution will not be actually a quadratic. If you work this out, it will actually be a third degree polynomial, but it has no constant term because we multiply with x here. So we still have 3 unknowns. That corresponds to the fact that there are 3 unknown. These undetermined coefficients correspond to the fact that we have 3 coefficients in a quadratic. But it's not a quadratic. It's a cubic because there's no y term. You might ask, why is this important? Well, you should try to not do this, and you will see what, or perhaps I'll give an example in the next one, you'll see where things go awfully wrong. Okay, now, knowing this, what happens now? Okay, the technique is now just the same as before. Nothing changes. We now take the derivative again, 3ax squared plus, what I was doing here. x cubed, x squared, x, right? Sorry, I put the wrong power there. 2bx plus c. That's the derivative, right? And the second derivative is 6ax plus 2b. Okay. So let's plug this into our equation, y double prime plus y. So y double prime plus y prime, that is equal to 3ax squared plus 2bx plus c plus 6ax plus 2b. Okay, that is fine. And that must be equal to this polynomial 3x squared plus 4x plus 2. 3x squared plus 4x plus 2. Notice that what we have here on this side is a polynomial of degree 2. This might surprise you a little bit because you started plugging in a polynomial of degree 3, right? How come we don't see the polynomial of, why is this the result of the degree 3 here? We started with a polynomial of degree 2 here, right? This was a polynomial, sorry. Here, this was a polynomial of degree 2 and we plugged it in and we got a polynomial of degree 2 after plugging in. Here we plug in a polynomial of degree 3 and we also get a polynomial of degree 2. Why is that? Well, that's exactly because there's no y term. Y prime, look at the degrees. Y is degree 3, y prime is degree 2, y double prime is degree 1. The degrees go down, right? Since there is no y term, there is no degree 3 part. And that's exactly why we have to compensate. We won't have the highest, this thing, the degree 3 will not appear. So that's the reason why we need to do this. Okay, so now we have everything. We know what we have to do. Let's group everything, sorry. So the powers, 3ax squared, what are the powers of x? We have a 2b plus 6a x, and we have a 2b plus c, and that is equal to 3x squared plus 4x plus 2. So the 3a is equal to 3. 3a is equal to 3. We see that 2b plus 6a is equal to 4. And 2b plus c is equal to 2. Okay, from this we see that a is 1. So from this we see that 2b plus 6 is 4. That means that 2b is equal to negative 2. That means that b is negative 1. And now we plug it in here. We see minus 2 plus c is 2. So we see that c is 4. I hope I went rather quick. But I hope I didn't make a mistake. Anyways, the technique is that's the technique. So we find the solution and we see the solution is actually of degree 3. So our particular solution here is x cubed, that was 1, a was 1, b was negative 1, so minus x squared plus 4x. Okay, now let's work back to the homogeneous solution. So let's get rid of these little arrows here. So let's go back here. We didn't finish this thing because I wanted to show you what goes on here, but this is also quick, right? We know what the standard solution look like. What are the roots? 0, so there is e to the power 0 times x, and the other one is e minus 1x, right? You multiply the roots become the coefficient in front of the exponent, in front of x in the exponent, and then we take a general combination of that. Now what is a to the e0 times x? That is just a, right? So here we get a constant and here we get minus x. So this is how the homogeneous solution looks like. Okay, so again, the fact that t is 0 has this effect here on homogeneous solution, but that is not, shouldn't look there. Okay, so now what's the general solution? Would be to combine the two, right? Y equals x cubed minus x squared plus 4x plus a times a plus b e to the minus x. And did I give initial conditions? No, I didn't say initial conditions, so let's leave it that way. Okay, so this is what when there is no y term. Now you can say, Professor, this one had no y prime term. Why didn't we do anything with that? Oh, that's okay. I will see examples where there are all three terms. So it is the y term that matters. But there is one more case, and this is this case here. Y double prime equals 60 x cubed plus 12x plus 4. So what is now going on here is, according to our scheme, we should put in y equals general coefficient. This is degree 3, so we should put in a degree 3 polynomial of general coefficients, right? This is what we should do. That's the general coefficient, degree 3. But what we have now, no y term. So that's already something. So we have to multiply with x because no y term. There's also no y prime term. So we have to actually compensate again, and that's an x squared. So if we use the method of indeterminate coefficients, we have to not actually give a general polynomial of degree 3, but a general polynomial of degree 5, where there is no x, and if you expand this, so it would be a x to the 5th plus b x to the 4th plus c x cubed plus d x squared. Notice there is no x term and there's no constant term. Because we at the end we have 4 coefficients that correspond to the 4 coefficients that, well, this one is 0, the x squared term, but right. So this is how our solution has to look like. So recapitulating, if there is a y term, so here it was so obvious that I didn't say, there is a y term. If there is a y term, then we just take a general polynomial, undeterminate coefficients of the same degree. If there is no y term, then we take again a polynomial of the same degree and multiply it with x. If there is no y term and no y prime term, then we take a general polynomial of the same degree, this is now 3 here, and multiply with x squared. But this can be quicker. You can just work this out, but this is a double antiderivative problem. If I would have given you this in calculus, you would never do this undetermined coefficient. You just say, okay, I integrate twice. So we see that y prime is the antiderivative of 6x cubed plus 12x plus 4 dx. So that would be 60. That would be 60 power rule 60x to 4 divided by 4 plus 12x squared divided by 2 plus 4x plus a constant. Okay, but we're looking for a particular solution, so I don't need to keep track of the constant. So I can take the constant 0 here. So it's a particular solution. I'm going to write this because there is nothing there, but there's the reason there's nothing there. Particular solution, so no constant needed. No constant needed. But this only once. We have to do it one more time. We enter drive again. 60 divided by 4 is 15, right? 15x to the 4th plus 6x squared plus 4x dx. Let's enter drive. 15. Add 1 to the exponent, divide by the exponent. Add 1 to the exponent, divide by this exponent. Add 1 to the exponent, divide by the exponent. And again, no constant term needed because we are not just a solution. Now we simplify. 3x to the 5th plus 2x cubed plus 2x squared. That's our solution. And you see, oh, but why is there only 3 terms? Didn't you say there were going to be 4 terms? Yes, but there is one term is 0, right? There is no, what you're missing is the 4th degree term here. So if you would work this out, you would get a system, equations in A, B, C, and D. We would have solved for this system, and we would find that A was 3, B is 0, 2, C is 2, and D is 2. But that is more work, right? If we are in this case, we just enter drive. But technically, this is what's happened, and I want to say it this way because if you ever have to do higher degree differential equations, it's the same principle, right? If you have to do a third order equation with linear coefficients, with linear third order equation with constant coefficients, you would have to do the same thing. But okay, so this is all in the case that alpha is 0. What if alpha is not 0? So I'm going to again look at an example here. Let's take the example here. Y double prime minus 3y prime plus 2y is e to the 3x minus 1 plus 2x plus x squared. Yeah, they write it in this order, doesn't matter. And was there an initial value problem? But I'm going to make one. So y0 is 1 and y prime 0 is 2. It's probably going to give some fractions, but that's not okay. Okay, let's start and see what we need to do here. Step 1 is, of course, the complementary homogeneous. That would be y double prime minus 3y prime plus 2y equals 0. And so immediately, because it's constant coefficients, we do the characteristic equation. Only when it's constant coefficients, we get t squared minus 3t plus 2. Of course, there could be any x's in here, right? That would not be an equation, right? Okay, so we can factor this. t minus 2 times t minus 1. Are we all on board with that? Okay. So we find the roots. The two roots are t equals 1 and t equals 2. So we know that the general solution, homogeneous solution, looks like A times, we take these as the coefficients of Ex. Well, I mean to say in the power. So E 1 times x plus B E 2 times x. Okay, this is the 1 and 2 go, where the 1 and 2 go. Okay, that's step 1. Step 2. What do we do now? We have this alpha. So alpha is not 0. And now we use the variation of parameter technique. Variation of parameters. So, oh my God, Professor, a totally different method. Be patient. So what does that mean? I'm going to do y is equal to u to what? Well, I'm going to only take, so in general here I write the formula. I'm only going to take the exponential. So not the polynomial, right? So the general form, remember, is this. This is how it look. That's how the general form looks like. But for the moment, I'm ignoring the polynomial and I'm only taking the exponential. Okay, but this u is going to be our parameter. So this is the parameter that depends on x. That's what that means, right? It depends on x. So we're gonna, when derivatives, there are real derivatives here. So this is, in this case, what was it? 3x, right? Yeah, e to 3x. Okay. And what do we do? Well, we know what we do. Once we make this decision, we know what to do. We calculate y prime, that is, take the derivative of the first, copy the second, plus that, and there's a 3. If e3x, the derivative is 3 times e3x, chain rule. And now the double derivative, now we have two terms, we have to do each separately. The derivative of the first factor, copy the second factor, plus copy the first factor, take the derivative of the second factor, let me put the 3 in front. Do the same here, 3u prime e3x, and now I take the derivative of the second, that's another 3, so 9u e to the 3x, right? 9 is from twice coming, another 3 comes down. We plug everything in, so we want y double prime, so there's u double prime. One thing, yeah, sorry. Now at this point, and only at this point, notice what has happened here with this exponential. I just want to point out, this exponential is everywhere, and it's also on this side, right? There's more on this side, but it's also there. There's also more here on this side. And that's the point. So what we're going to do is I'm going to already factor out that exponential, the e alpha x, right? In general, alpha here, so here alpha was 3, perhaps I should say that alpha was 3 here, right? That we factor out, and let's see what we have here. We have y double prime, so we have this one, right? But I'm already factoring out so u double prime plus 3u prime plus 3u prime plus 9u. Okay, so this is everything that comes from here. Then the y double prime, that is minus 3 times, right? So it is minus 3 times u prime plus 3u. The e3 axis is all factored out in the beginning. Okay, the first time you might not see this, but if you think about it, this is always going to happen. And that's why it's much easier to write down if you factor it out right away. But only then. Not factor it, you say, oh, if it's so unimportant, why do we even take it? It plays a role, right? Why does it play a role? Because while we're taking derivatives, okay, nothing happens here, nothing seems to happen here. No, that's not true, because an extra 3 came here, and that 3 is exactly this 3, right? And here actually a 9 came. So this exponential function does change things, but eventually we can factor it out. So we cannot factor it out, we cannot cancel it in the beginning. At the end we can cancel it. Going on. So I plugged in y prime, but there's still plus 2y to plug in, right? So that is the blue part here, so this one. So plus 2 times u, because again e3x is factored out. And that is equal to e3x times, and that was this polynomial here, where was it? X squared plus 2x minus 1. Let me write it in the form. I don't know why they write it this order. All right, prefer to write things in this order. So now, as we said, this exponential cancels. Okay, let's group things together. What do we have on the right and left hand side? We have a second order constant coefficients in u. Okay, let's write down what it is. So there's a u double prime, then there's a 3u prime, a 3u prime, and a minus 3u prime. So there's in total a 3u prime left. and then we have a 9u minus a 9u, they cancel out, but there's another plus 2u. You ask, is this the same as the original equation? No. Okay, it happens to be 3 is minus 3 and 2, the numbers seem to be same, but really that's not, everything can happen here. It's just bit coincidence that the numbers look the same. They're not even the same, but they look the same. So that's on the left. What do we have on the right hand side? Well, we have a polynomial. Ah, professor, but that we did that before. This is exactly what you were doing first, right? This is the case where there is no alpha anymore. So we don't have to worry about this. We know how to do this. I mean, we have to worry about it. We know how to do this. Okay, let's do this then. If you know what to do it, then we do it. Okay, here we go. So, so now we use the propose. Remember, what is it that we have to propose? Okay, it's going to be u now. A polynomial of the same degree as the forcing functions, but with unknown, undetermined coefficients. And then was this business of multiplying with x. Is that an issue here? No, because there is a, not y term, there's a u term, right? The characteristic equation, it would be t squared plus 3t plus 2. There's a constant term there, right? So if this term would not be there, then we have to multiply with x. If both of these terms were not there, we have to multiply with x squared. But then, okay, we'll do examples of that. So this is just the standard way, and then we know what to do. Let's do it quickly. U prime, that is 2ax plus b. U double prime is 2a. We plug this all in. 2a plus 3 times 2ax plus b plus 2 times ax squared plus bx, so only 2, plus c equals, and then we have the left hand side x squared plus 2x minus 1. And we know now two polynomials of the same degree, right? Both are of degree 2, and we have to compare coefficients. So let's order this one in the right order. So we have 2ax squared. What are the x terms? We have an x, we have a 3 times 2, that's 6a here, this one. And we have a 2 times b, so plus 2b. Plus, and what else do we have? The constant terms, we have a 3 times b, don't forget there's a 3 in front of here, right? And here is a 2 times plus 2c, and that is equal to x squared plus 2x minus 1. So compare coefficients, 2a is same as that one. So 2a is 1. This one, 6a plus 2b is equal to 2. And 3b plus 2c is equal to negative 1. Okay, and I have to solve. Okay, a is a half. Bit annoying, but okay, it's okay. If I plug it in here, that is 3 plus 2b is 2. So we see that 2b is minus 1, so b is minus a half. So we plug the minus a half. We plug this in here, we get minus 3 halves plus 2c is minus 1. So we see that 2c is equal to 3 halves minus 1, which is a half. So c is equal to 1/4. So our solution is u equals a half x squared minus a half x plus 1/4 plus 1/4. Is that the solution? No, that's u. Okay, what is y then? Ah, well, we said what y is. We put y equal to this thing. So this is multiplying this with, so y is now equal, the particular solution is equal to a half x squared minus a half x plus 1/4 times e3x. And so the general solution, last step, the general solution is now you take the particular solution, a half x squared minus a half x plus 1/4 e to the 3x plus the general homogeneous solution, that was this guy here, a ex plus b e2x, right? Yes, okay. All right, that's it. And if there, I did say initial conditions, right? Did I give one? Yeah. This was this guy, right? So if x is 0, then y is 1 and y prime was 2. Okay, let's plug this in. So this is y. If I plug in the first, y equals, well, we have a 1/4 e to the 0 plus a plus b, right? If you plug in 0 in here, these exponentials disappear. That's one equation. Now we have to take the derivative of this. So let's put this here, y prime. That is the derivative of a half x squared, that is actually x, right? 2x squared over 2 minus a half times e to the 3x. Now, be careful, this is a product, so we have to do the product rule here. So this is the derivative of the first time the second, plus, copy the second, x squared minus a half x plus 1/4, 3 times e3x. Okay, and then plus aex plus 2be2x. And if I plug in now, I should get 2 here. 2 is equal to, this is 0, so we get minus a half. This will be 1. This whole thing is 3/4, because this is going to be 0 again. And then here we got another a plus 2b. Okay, so okay, so what do we get here? I don't like fractions, so let's multiply everything with 4 here, both equations. So get 4 is equal to 1 plus 4a plus 4b, and then 8 is equal to minus 2 plus 3 plus 4a plus 8b. You follow? Multiply everything with 4. And then, so perhaps we bring the constant to the other side, so 3 is equal to 4a plus 4b, and then here we get 1, so 7 is equal to 4a plus 8b. And here the method of elimination is the more desirable one, because I don't want to solve for a. The substitution method is nice if there's no, if there's, well, I could have done the substitution method in this case, but then I was dealing with fractions. Okay, so I'm going to do this minus 1 and add it up there, right? So then this will come 4, this will come 0, and this is minus 4b plus 8b, that's 4b plus 4b. So actually we see that b is 1. Okay, and if b is 1, now I can plug this in here, let's say. Then we see 3 is equal to 4a plus 4. So we see that minus 1 is equal to 4a, so a is minus 1/4. So our solution is y equals a half x squared minus a half x plus 1/4 e to the 3x minus 1/4 e to the x plus e to the 2x. Okay, so let's look at the next example. Okay, so here is y double prime minus 4y prime plus 3y equals e3x, and I'm going to do a different example than textbook so that you can compare a little bit. I'm going to take here a degree 3 polynomial. It's going to be a little bit more work, but okay. But I'll take the coefficients a bit easier. And again, I'm also going to take initial conditions. y0 is 1 and y prime 0 is also 1, just for simplicity. Probably the numbers are going to be ugly, but that doesn't matter. Okay, so step 1, the homogeneous, the complementary equation. That would be y double prime minus 4y prime plus 3y equals 0. That has a characteristic equation because it's a constant coefficients. So this is t squared minus 4t plus 3 equals 0. So this has to factor as t minus 1 times t minus 3, right? Two numbers that multiply to 3 add up to -4. That will go these two guys. So t is 1 and t is 3. Okay? So we know that the homogeneous solution looks like a times e to the 1 times x plus b times e to the 3 times x, e3x. Great. Step 2. In step 2, since we have, so alpha is 3 here, what we need to do now is use our variation of parameters. So variation of parameters technique, right? It basically means introduce this u here, but in a special way, it is going to be this way. Alpha is again 3, it's the same as before, but that's why it doesn't, it depends on what alpha is, right? So we took another example here with alpha 3. This is how we're gonna try to find a solution of this form, okay? And we know that this will transform into something nice, as you'll see again as before. So let's calculate everything here. That's u prime e3x plus, well, we actually done this, so we could have copied it. Yeah, can I cheat? I'm gonna cheat, right? I did these calculations, right? I did this here. I'm lazy, man. So I'm taking these ones and I'm copying these two here. Copy, and I'm gonna paste it here because it's exactly the same, right? Let's use the fact that we had the same alpha. Now, of course, in general, this will not be the case, but in this case, I'm lucky to have this. Okay, so now I can plug this into the equation here. So in this equation that you should see on top there, so that is, again, but another thing is we know that we can factor out this e to the 3x, and then what we have left. The y prime, the contributions are a u double prime plus a 3u prime plus a 3u prime plus 9u. All the green stuff, right? But without the 3x that is factored out. Then minus 4 times y prime, that is the orange stuff, that is the u prime plus 3u, and then plus 3 times u, y itself, that is just u here, okay? And that is equal to e3x, x cubed plus 1. Okay. So, the whole point of this is that you get rid of the exponential, and now you get something that involves polynomials, and that's the method of undetermined coefficients. Okay, so, but let's gather everything again. U double prime. Now you can copy from the previous thing because it's a different equation, right? The numbers here, the coefficients are different, so don't copy now. So 3 plus 3 minus 4, that is 2. And then we have a 9u minus 12, don't forget that, plus 3. Oh, that's 0, right? Oh, okay. So this is 0, okay, equals x cubed plus 1. Okay, Professor, this is something, is this not a case where we have to be careful? Yes, exactly. There's no u term, so no u term, and this means that our proposed solution, so this is step 3, right? Here we're going to propose in indeterminate coefficients, and it's a degree 3, so we have to do degree 3, x cubed plus bx squared plus cx plus d, but no u term means we have to add an extra x here. Okay, all right, okay, if that's what it is, let's see. Well, I should multiply this out, right? Because you don't want to do product rule and things like that. It's first of all going to be messy, and secondly, you don't want to do that. Okay, so u prime is equal to 4ax cubed. Luckily, this is not so hard, right? This is just a little bit writing down, keeping your cool. And then u double prime is 12ax squared plus 6bx plus 2c, right? And now we plug this in. U double prime is 12ax squared plus 6bx plus 2c, that's u double prime. Now we do plus 2 times u prime plus 2 times 4ax cubed plus 3bx squared plus 2cx plus d, and that has to be equal to x cubed plus 1. Now, we should have a third-degree polynomial on the left. On the right we have 1. What is about the left? And this is exactly what happens. We have here 8a, okay. So I don't want to introduce too many fractions here. I'm going to make this into 24. Okay, I'm changing it slightly. I hope that is okay. There's nothing, I've not used anything. I have not used it, right? I just want to get a nice coefficient here that I don't have to deal with weird stuff. So, okay, what we have? We have 8ax cubed. And that's the only cube term. What are the square terms? Well, there's one here, that is 12a. And there is one here that is, don't forget the 2 here, 6b. Then the x terms, well, it's a weird x here. It's 6b. And with the 2 in front is 4c. And then finally constant is 2c plus 2d. Don't forget that extra 2 there, right? Okay. And that is equal to 24x cubed plus 1. So this, we now compare coefficients, so it means that 8a is equal to 24. This guy, 12a plus 6b, has to be 0, right? Because there is no x squared here. 6b plus 4c, the coefficient of x, well, there is no x on the side there, that's also 0, but there is a constant term, so 2c plus 2d is equal to 1. I guess I should take here also, okay, let's let 1 fraction is okay. So what does this give me? This is a is equal to 3. If I plug in this here, they get 36a plus 6b is 0, 36, there is no a anymore, right? 3 times 12, yeah, 36, right? Yeah. So this means that b is minus 36 divided by 6 is minus 6. Okay, great. And then if I plug it in here, then now I plug the b in here, right? So I get minus 36 plus 4c equals 0. So we see that 4c is equal to 36, so c is equal to 9. Okay, so b, this is b, right? This is 9. And then finally I plug this in here. This is 8t plus 2d is equal to 1, so 2d is equal to minus 17. This is where I get a fraction, but that's okay, minus 17 over 2. So the solution is u equals a was 3, right? 3x cubed. This was the power of, let's see, where is it? Oh no, it's the power of x to the fourth. Be careful. It's the power of x to the fourth. And then plus b was minus 6. So minus 6x cubed. That's the, see, look here, right? This is where the u is. C is a coefficient of x squared, that is 9x squared, and d is the coefficient of x. So this is our solution for u. Is that a, no, we want y. So the particular solution is this guy times e3x. And now we also have the general solution, so step 4, I guess, or whatever, forget now where I am. The general solution is the sum of the particular solution, 3x to the fourth minus 6x cubed plus 9x squared minus 17 over 2x e3x plus, and the homogeneous one was, I'm reusing a and b, but that's okay because a and b are being determined here. So aex plus b e3x. And then step 5, the initial condition was if x is 0, then y is 1 and y prime is 1, I think I said. So that would be 1 equals. Now, this whole thing is gone. So this actually is nice, right? Because there is no x here. So this whole thing is gone if I plug x equals 0. So I get a plus b. Oops. And what else? And then, okay, I have to take derivative. So this is derivative. There's a lot of work here. The derivative of the inside function, the first factor, 12x cubed minus 18x squared plus 18x minus 17 over 2 times e3x plus 3 times this guy, 3x to the fourth minus 6x cubed plus 9x squared minus 17 over 2x e3x. The 3 comes from the derivative of e3x, chain rule, right? And then, so I did the derivative of the constant of this guy. Now the derivative of that guy is just a plus 3b e3x. If I plug in 0, what happens? This should be 1. The derivative is also 1. There's a term here, minus 17 over 2 e to the 0, that's 1. Again, this whole thing gone because there's all powers of x here. So plus a plus 3b. Okay, yeah, if I chosen a little bit nicer, then we wouldn't have to deal with this fraction here. So now we bring this to the other side. So this is plus 17 over 2, right? So this would be 19 over 2 equals a plus 3b, and 1 equals a plus b. So we can subtract the bottom from the top. 19 halves minus 2 is 17 halves equals 2b. So I'm subtracting this from, right? I'll write it this way now. So we see that b is 17 fourths. 17 fourths, sorry, sometimes I write by 1. I used to write by 1. In Europe they write the ones this way, but that's how you guys write 7. That would be completely confusing, right? But you see my 7, I put a little, that's how my 7s and my 4s look like. 74th, and then a is equal, you can plug this in here. Plug it in here, so 1 equals a plus 17 fourths. So that means, if I bring this to the other side, is minus 13 fourths is equal a. And if I didn't make any mistake, which is not guaranteed, I can write down the solution now. The actual solution here is with these two coefficients. But let's not waste time at writing it down. Of course, you have to do it on the quiz or in the homeworks, but I want to do one more example. I want to point out, why did this happen? Why was this a special case where there was no U-term? Could we have predicted this, or we just have to wait Doesn't matter really, right? You just do the calculations. But yes, you can predict this. Why? Look at this. T is 3 was a root, and alpha is also 3. So in other words, if alpha is a root of the characteristic equation of the complementary homogeneous, then you get this. This thing happens. Okay? So let's look at another final example. Let's see y 4y double prime. Let me see here. Sorry. Where is it? I want to take this up. No. Ah, 4y double prime plus 4y prime plus y equals e to the minus x over 2 3x. I'm going to make it a bit simpler again than the textbook, but I'll do, instead of that, I'll do again an initial condition, which I might change, because I don't want to have to deal with fractions. So at some point I might say, oh, I'm going to change this, okay. So, okay. Let's work on this one. Step 1. Complementary homogeneous. Okay, that is 4y double prime plus 4y prime plus y equals 0. Well, that has a characteristic equation that will determine the solution. That is 4t squared plus 4t plus 1, 0. Now we have to factor this. This is factoring. You can use the quadratic formula, but you can factor here the AC method. You take two numbers that multiply to 4 and add up to 4. That is 2 and 2. Okay? You can actually even go quicker, and that's what I'm going to do. So I told you how to do it with the AC method, but I'm not showing you. Try it at home. But this is also 2t plus 1 squared. I recognize this immediately as double product formula, right? The double product formula says, that's not that I want to do. Double product formula is take the square of this one plus the double product plus the square of that one. That's exactly what we get. So this tells me that t is minus 1 is the solution, and it's the only solution. Oh, that was a special case as well, right? Remember, that was a special case. Why? Well, we know now that the homogeneous solution in that case is, you take this minus a half again, that's all you always do, but you can only take it once. So what do you do for the second fundamental solution? You have to multiply that with x. So this is, so here, because of the double, this is what we call, this root is a double root. We have only one root. It kind of counts twice. Another way of saying, one says often this is a root of multiplicity 2, because it's the power 2 here, that in the factorization. Okay, but that's not so important. That's what happens. Okay, sure. Step 2. Variation of parameters. I'm going to look for the solution. Oh, what is alpha here? Alpha is minus a half. That's the same as the root here, and we said that it's going to give something weird. It's going to happen, right? So we know already that something is going to happen here. From the previous case, we have seen that if alpha is a root of the characteristic equation, then the u, we're going to get a differential equation in u. Where is my differential equation in u? Where did it go? No, where was it? Sorry, I went too far, right? No. Where did it go? Here, right. Without the u term. Okay, so this is going to happen. Okay, I'm ready. So minus a half x, right? So it's the same alpha that we use here. So y prime, now we have to, I have to do the calculation. U prime is minus x over 2. Let me write it that. Minus a half u e to the minus x over 2, right? Because minus a half comes out. And then y double prime is u double prime e minus x over 2. We get minus a half u prime e minus x over 2. That's the derivative of the second factor. And now the second term, if I take the derivative of the first factor u, that becomes a u prime. And if I take the derivative of the second factor, we get another minus a half, that comes plus 1/4 u e to the minus x over 2. Okay, so we put everything into our equation. So we have 4 times the, but no, sorry, let me do this first, right? This is, we know that we can factor out, I'm going to write it in a big parentheses here, this e to the minus a half x. Yeah, sorry, let me, e to the minus x over 2, right? Again, it's everywhere there, so I just factored out. So what is it then? I have 4 times y prime, that is, there's a u double prime there, minus a half u prime, another half u prime, and 1/4 u, okay, plus 4 times y prime, right? That's this term now. That is, there's a u prime there and a minus a half u, and then just plus y, which is just a u, because I factored out the e fact part. And that is equal to, what was the, this is equal to this guy. E minus x over 2, what did I say, 3x? 3x. So these cancel, shoop, shoop, and we have what we expect. We're gonna have a differential equation with just polynomial as a forcing function, a second order. So let's work it out. So we get a 4u double prime, and here these 2 minus a halves that combine to minus u prime, but it's times 4, so minus 4u prime. 4 times 4, there's a plus u here, so I'm just expanding the 4 here, plus 4u prime. 4 times 2, that's 2u. Yeah, plus u. Okay, and that is equal to 3x. So let's see what we have. Yeah, the u's cancel, you were right. We expected that. It's exactly what we expected. Hey, professor, but also the u primes cancel. That's something I didn't expect. Yes, that's exactly what happens now. Because not only is alpha a root of the characteristic equation, we know that something's going to happen. It's the only, this equation itself is only one root. That's again special. So it's doubly special. So that's why we get a doubly special equation here. 4u prime is equal to 3x. Now, I said I'm going to change the numbers a little bit to make them nicer. I kind of, so okay, this was supposed to be an 8, guys. Yeah, okay. Yeah, nobody saw that, okay? Okay, that was an 8. Okay, for w prime is equal to 8x, so that means u prime is equal to 2x. So the method of indeterminate coefficients would say, okay, what would it say? It would say you have to do a general polynomial of the same degree, which is a linear polynomial here, and then multiply it with x squared now, right? Because there is no u term and there is no u prime term. So we're going to get a solution of this form. Yes, but come on, guys. Let's just do in this case, it's just simpler to do antiderivatives, right? So what we get is, it's not really a differential equation. It's something that you did in Calc 2, in Calc 1 even. So u prime is equal to x squared, right? And then u double prime would be x cubed over 3. And again, I don't need to take constants because I'm looking for a particular solution. So again, constants are not necessary. And this is exactly of this form, right? Except that there is no b, but okay. But you see, the solution is a cubic, right? Although the original was just a linear there. So yeah, okay. So this is the particular solution. So u is equal to x cubed over 3. Oh, sorry. Okay, I hope that was not confusing. I was antideriving, right? So I'm taking antiderivative. I'm taking the antiderivative here. So this was the antiderive, right? It was so simple that I didn't even write down the integral signs here. So this is x cubed over 3. So y is x cubed over 3 e to the minus x over 2. Don't forget there's an extra guy there, right? And so now step 4 or 3 or whatever, 4 I think already. The general solution is this particular solution. And again, that's why I didn't need to bother about integration constants, because only needed 1. Plus the general solution, which, by the way, was special too because of this being a double root there, right? Or the only solution. Minus x over 2 plus bx e minus x over 2. Okay, so in fact here you could even factor out the x minus x over 2 everywhere, and so we would have an x cubed over 3 plus a plus bx. It makes it slightly simpler in calculations, especially now. Let's do the initial conditions, right? So if x is 0, then y was 1 and y prime was 1, but I'm going to probably change these numbers a little bit. So let's plug this in first. 1 equals, the whole exponential goes, we get a plus, we get just a, because this is a power of x, this is a power of x, so I just get that. Okay, that's good. So I do have to take the derivative of this guy, so let's take the derivative here. That's y prime is, well, the derivative of the first is minus a half e to the minus x over 2 x cubed 3 plus a plus bx plus, and now I just copy the exponential and take the derivative of that guy, 3x squared divided by 3, that's just x squared plus b. And now plug in x equals 0, what do we get? Well, let's see. So if I plug in 0, I'll determine what I'm going to take my y prime yet. So y prime is going to be some number here. Okay, I'm going to change it a little bit so that we don't have fractions. No, okay, let me put it. There's going to be a fraction. That's okay. 1. What happens if I plug in 0 here? Well, the only thing that survives is the minus a half and the a. Right? Everything else is either the exponential becomes 1 and the x's are 0, and in the second term only the b remains. And I know that a is 1, so I get 1 is equal to minus a half plus b, and so b is equal to 3 halves. And that's the solution, so that right up, this is the last thing I do. And then the rest I leave for you to do homework. So the solution of this initial volume problem is x cubed plus 3. A was 1, right? Yeah. Plus 1 plus 3 over 2x. Okay. So, just recapitulating, we try to solve polynomials of this form, differential equations of this form. We first do this. You do the complementary equation, right? You do. Let's look here in the general case. We do the complementary equation. We sorry. Now jumping a little bit, sorry, let me go to where we were doing things. Here, right, this is an example. We do the complementary equation. This next step is variation of parameters, where we now introduce the exponential, right? Now, what is going to be important is this alpha, the coefficient in front of the power of x here, is that a root of the equation or not? It can be not a root, it can be a single root, or it can be even the only root. Okay, there's the 3 different cases, and the result is always the same. We will end up with a differential equation, a linear differential equation with constant coefficients, in which the right-hand side is now just a polynomial, and that one we solve with finding a general polynomial undetermined coefficients, but we have to be careful. If there is no u in our differential equation, then we have to multiply with an x here. So that was the case here, right? So here we see that we had to add the x to make up for the right thing. And even if the root was, if alpha was the only root of the characteristic equation, then we even had to multiply with x squared. So this was our general form, but in that case, don't do that because it's much more work. It's much simpler to just do the double antiderivative. Okay, that's summing it all up.